In this section, we look at how magnets can help maglev trains travel with less friction. We'll need to investigate the properties of magnets and electromagnets to figure out how they cause a maglev train to float above the track. Let's look at cause and effect a little more closely. Like everything in NGSS, we realize that there's a progression of understanding. At the earliest grades, like the elementary level, we want students just to recognize that events are related. A young kid just grasps tangible actions like, when I pushed the car, it moved. Then we move on to the big systems level causes, like I must have somehow given the car energy, which caused it to move. As we progress towards high school, we start to explore the mechanisms. How does that energy transfer happen? My hand applied a force to the car, which pushed back with an equal and opposite force. We can actually illustrate this progression from simple cause and effect diagrams. For our maglev train example, we know that it uses less energy. But what causes that? Well, it's floating above the tracks, so it uses less energy. This is the basic level of cause and effect. But what causes the train to float? We can add a new box and know that there are magnets on the track that cause it to float, which causes the maglev train to use less energy. But how do the magnets cause it to float? We can add another box, a deeper level of understanding. And we know that in magnets, like poles repel. But then we want to know about how does floating above the tracks, how specifically does that enable a train to use less energy? We add another box and we can fill it in by saying that there is less friction. You can keep adding more boxes to get a deeper and deeper level of understanding. And now cause and effect is not just a simple two-box statement, it's an entire chain. So let's see if we can help students fill in the boxes for our maglev trains. We check in with our unit roadmap at the start of lesson 5.15. Then we introduce maglev trains and discuss what the advantages and disadvantages could be. Then students receive a handout that guides them through 3 stations to build their understanding of magnetism. In the magnetic cereal, students find that there's actually magnetic material hidden in the crumbs of most commercial cereal, and that they can attract them even when the magnets are not touching the cereal. In the magnets on a stick station, students can arrange the magnets in such a way so that one magnet floats up above the others. This is the principle that's going to drive the maglev trains. And in the magnetic train station, they build a model of a simple train and see how it can move floating above a track of magnets. In lesson 5.16, we investigate magnets, discover magnetic fields, and determine the strength of a magnetic field. We start off by just marveling at how the moon controls Earth's tides without even touching it. That's a lot like magnets. It's a non-contact force. We explore how magnets have 2 poles that affect their interactions. Students then investigate the strength of this invisible non-contact field using the Pocket Lab Voyager. How does its strength depend upon its distance away from the magnet? We end up discussing what we've discovered about fields and how they might improve transportation. In lesson 5.17, we ask, could we use magnets to push a vehicle? We watch a video about an innovative and experimental transportation technology called a Hyperloop that uses magnets to push it along its path. Students then build and test magnetic accelerators using the instructions in a handout. They share out their different variations that they created and show the data that they graphed. Students end by revisiting the maglev train phenomenon. How do magnets help it move more efficiently? All the magnets that we've used in class so far have been permanent magnets, but there are also magnets that we can turn on and off. We'll use a battery, coil, and nail to discover how the design of this electromagnet affects its strength. In lesson 5.18, students learn about electromagnets and ask, what factors affect the strength of an electromagnet? How can I build a stronger one? They work with 2 stations. In one, they compare different electromagnets to see which one can lift up the most paper clips. The goal of the second station is to understand a little bit more about how an electromagnet can use electricity to create a magnetic field. In that second station, they use a magnet and a coil and see that they can actually create electricity. They discover that a relationship between electricity and magnetism goes both ways. We learn more about this relationship when we look at the phenomenon that a compass needle deflects when a current flows through a wire nearby. In lesson 5.19, we introduce students to the compass deflection phenomenon. While it's kind of annoying if you're trying to use your compass to navigate, it's actually really useful in today's world of electric cars. That's because batteries overheat if too much current flows into them too quickly. So we need a way to measure electric current. Students are going to use a wire, nail, and a compass and some batteries to build a simple ammeter that measures current. The more the compass needle deflects, the more current is flowing through the wire. Students reflect at the end on the cause and effect relationships that they've seen. In Lesson 5.20, we bring things back full circle. We started the unit comparing the efficiency of different vehicles, and now we're back there again. We use the unit roadmap to relate all of our activities together and watch a brief but inspiring video about the world's most efficient vehicle. If you thought your bike was efficient, you'll love this one. Then students wear the hat of transportation engineer and must recommend the most efficient transportation option for each scenario in the transportation scenarios handout that they get. Finally, students participate in unit concept checkpoint number 2. Our students are finally ready for their culminating experience, and that's up next.